Welcome everyone. This is the second part of lecture number 9. This one is on object detection and a very famous object detection network called YOLO. Object detection now is the task of not just telling what is in the image, like image classification. It also tells you about where in the image those objects are. So for example, using bounding boxes, the probably most famous approach of localizing the position in spatial dimensions of objects with 4 numbers, x, y, and width and height of those boundaries here. We can think of this task as an extension to the classification idea, right? So an input is an image, then we have some convnet, and in the end we'll have an output vector that corresponds to the class probability, for the input being a dog and a cat and all these things. We can also think of the network then to produce 4 more values that are not categorical variables, but continuous ones. So x, y, that is the, let's say, center position of the box, and w, h for width and height of that box. Now, this question would be then, okay, how do we, train that network? How do we, or where do we even feed in the gradient? And that's simple. We usually formulate a total loss, like loss function that contains both parts. So a loss that quantifies how well this class probability vector has been predicted, and the regression loss, which kind of quantifies how well those bounding box parameters have been mapped. Now, what about multiple objects or multiple object types even, so multiple classes in multiple locations where these bounding boxes can be found? And I'm going to spare you the details about the different options that you have, because YOLO is the, I think, simplest kind of approach to this, and also because of that is very famous and known in the world. YOLO kind of uses a grid on the input. So we have an S by S grid. I think the paper was 7 by 7. And each grid now is responsible for containing the parameters for the bounding box and also the class probabilities. And after like a post-processing step of the results, we'll obtain those bounding boxes. And how exactly that works is or will be covered in the remainder of this short video. So what we'll use is a very simple convolutional neural network. So this convnet maps an image, and I have disregarded all the details about that convnet. You can find that in the paper. But it maps the input image to a activation vector with a fully connected layer, and then maps this activation back to the 7 by 7 grid. Now, this grid contains a couple of numbers, and if you zoom in on one of those things, let me just use my pointer. So if you zoom in on one of those things, this block contains B bounding boxes. So I think the paper used 2 bounding boxes per grid cell, and each of these bounding boxes obviously needs to be represented by 4 numbers, so x, y, w, and h, and also comes with a so-called confidence. So that grid cell and that bounding box detector, so that blue part here, can encode its confidence about whether there is an object or not as can the second bounding box detector, represented by the next set of 5 numbers. And then what type of object that is encoded in that last part. So those are the class probabilities here. No? You will find different formulations, but the original paper states that X, Y, and also W and H are normalized, so between 0 and 1, and X and Y are relative to the cell center, right? So that's something that the network needed to generalize better to the problem. So let's have a look at those grid cells again. We are given a set of labels. This time we have bounding box coordinates and width and height and a corresponding class label. And in YOLO, we have the 7x7 grid, and only that grid cell that contains the center of this box now is supposed to be predicting that set of parameters for the box, and also for the class probabilities. Yeah. So I just added on that nice figure here that is from the original YOLO paper, like the center point detection. And so these 2 grid cells are responsible. Now, in training, we have to be aware of which grid cells to look at, and that's exactly done like I just did here visually. And then we have to optimize, a little complex loss function. But if you look at every part closely, it's pretty intuitive and pretty clear what is done here. So the total loss function now is a set of parts that are added on top of each other, right? So the first part covers the X and Y coordinates, so we want to minimize that loss. So obviously the position of that box should be as close as possible to the given labels. We have this indicator variable that states that is 1 only if if I, which iterates over all of these S by S cells, if that specific cell is actually responsible for the object, and J iterates over all of these B, so in the paper 2 bounding box detectors, and that assignment now is made just by looking at, okay, that's the prediction of the bounding box for that bounding box predictor, and that is maximally overlapping with the given ground truth bounding box. Then that bounding box detector is responsible, and that's the one that we'll optimize. Yeah, the other one is disregarded. So in the beginning, you would randomize your weights, and we would start with some random predictions. You probably therefore choose randomly the bounding box detector that is closer to the actual target, and then you do the same with the width and the height of the bounding box with the same kind of indicator variable, and those 2 parts of the loss are given a specific weight called lambda coord, because we want to have like a relative calibration between those loss terms. There's another thing, lambda no object, and that is for the confidence scores of those cells and object detectors in the case that there's no object, and another term for the case when there is an object in that cell. And this term here is the quantification of the class probabilities, right? So the labels here will be a 1 hot encoded vector. So all classes are 0 except that one class that this box was labeled with, and the p hat here is the vector of predicted class probabilities. And then this whole, this total loss is then minimized in training. So although at that time YOLO wasn't even the best object detector, have a look at the prediction here that they even show in their paper. YOLO was adopted widely, and that was, I think, because it was simple. It was, end-to-end training. There was no, complex computer vision pipeline. Previous networks required so-called region proposals. So, steps in the image processing pipeline that kind of generated candidate regions that this could be an object, or this could be an object, and then a classification network on top of that. No, YOLO was end-to-end, image in and then boxes out. And I think the simplicity of this idea, and also the fact that YOLO could run in real time, or even above real time. So I think there were smaller versions of the network that could run in 140 frames or so per second at that time. I think that those 2 points defined the high rate of adoption, and YOLO, I think, pops up as one of those first results on Google when you look up object detection. All right, so just like any popular movie that gets a remake and a sequel and a prequel in different versions of the same idea, you will find many versions of YOLO. I call those YOLO evolution, and I invite you to read about how that went. So the first author of YOLO published 2 more versions, and then in the end said, I'm going to move away from computer vision and object detection because it's such a controversial field, because those things can be applied in the military and for applications I don't want to have anything to do with. And so there are follow-up works, and then even stuff that wasn't published as a real paper. So I think this is a really interesting kind of side note. I invite you to read about that and even find out about the details of the story. That was the end of this short video. YOLO isn't something that you are supposed to implement. That's just something I wanted to share with you. I hope you enjoyed that. I'm happy to answer questions on Wednesday. See you then. Bye.